Hey, this is Horner, and this is part 2 of the chapter 13 and 14 problems for temperature and heat. We're going to deal with specific heat of gases here. I've got a cylinder that contains 250 liters of hydrogen gas at 0 and a pressure of 10 atmospheres. They want to know how much energy is required to raise the temperature of the gas to 25 degrees Celsius. So in order to do that, we know that from chemistry. We have an equation, the ideal gas law, that is PV is equal to nRT. P is pressure, V is volume, N is moles, R is the constant, gas law constant, and T is temperature. So I can find moles very easily by just taking pressure times volume divided by the R value times the temperature. We also know that the change in the internal energy is equal to the number of moles times the heat capacity at a constant volume times the change in temperature. So that's equal to PV over RT. So that's what I filled in for N. Notice I took the N here, filled it in here, and we take that times CV and times delta T. So let's go ahead and plug everything into this equation. Our pressure is 10 atmospheres. We know that we have 250 liters of this gas, and we want to convert that to cubic meters, so that's 10 to the negative third cubic meters in every liter. Now at this point what we're going to do is multiply times the 20.4 joules per mole times a Kelvin. That's the constant. That's the CV constant for hydrogen gas. And that's that, it's a diatomic gas, so that's why it's 20.4. And then this is times 25K. We're going to divide all of that by our R value, which is 8.314 joules per mole Kelvin. And then we have 273 plus 0K for our temperature here. So we're going from 0 to 25, so that's our temperature change, essentially is what we're doing here. Now what we'll do is we're going to say that is equal to 57 kilojoules. So that's number 26. Let's go ahead and take a look at the next one, which is number 34. So this is a phase change. So in an emergency, it's sometimes practiced for medical professionals to immerse a patient who suffers from a heat stroke in an ice bath, a mixture of ice and water that's at equilibrium at 0 in order to reduce the body temperature. So we have 75 kilogram patient, the temperature is 40.8. We want to know we want to reduce that temperature down to normal range, how much heat needs to be removed. And then if she's placed in a ice bath that has 7.5 kilograms of ice, is there enough ice remaining in the bath when her body is 37 degrees? If so, how much? If not, what will the final water temperature be? So for letter A, we just want to find out Q is equal to MC delta T. We want to find out how much heat needs to be removed, so we're solving for Q. Her mass is 75. Specific heat of the body is about 3.5 times 10 to the third. And then we have 37 minus 40.8 for our temperature change. So that would be negative 1 times 10 to the sixth joules of energy. So it's about 1 megajoule or so. For letter B, we know that Q is equal to M, the mass of the ice, times the latent heat of fusion. So we're just trying to take all of the heat and that really warm person, we're trying to reduce their body temperature, so we're going to melt ice. It's probably the easiest way to kind of explain it. So this is equal to 7.5 kilograms of ice times 333.7 times 10 to the third joules per kilogram of ice and energy. So that would remove about 2.5 million joules, megajoules. So that's enough. It is enough. Since it's enough, we need to figure out how much ice we're going to have left. So the mass of ice is going to be equal to the amount of heat we want to remove divided by the latent heat of fusion. We only need to remove 1 times 10 to the sixth joules, so 1 million joules is what we said for that temperature change. And we know the latent heat of fusion is 333.7 times 10 to the third joules per kilogram. So that gives us a mass of ice of about 3 kilograms. So the ice that we have left, so this would be the ice that remains, is equal to 7.5 kilograms is what we started with, minus the 3 kilograms gives us 4.5 kilograms of ice remaining. For the next problem, which is number 37, it says how much heat is required to change 1 kilogram of ice, originally at -20, into steam at 110. So we've got to think about this. Remember, we had our curve. We're starting with ice, so we're moving up to, we're starting very cold ice. This would be 0 degrees, and this would be 100 degrees. We're doing Celsius here. So we've got to heat the ice up, then we have to do the latent heat of fusion, and then we've got to go ahead and move that up to water. Then we've got to start to boil that, and then we are going to move that up to steam. So I've got 1, 2, 3, 4, 5 things that need to happen here in order for this process to happen. So right here we are doing MC delta T for ice. So this is for ice. This is M times L latent heat of fusion. And then this is MC delta T for liquid water. This is the boiling of water, so that's M times LV, the vaporization. And then finally up at the top we have MC delta T for steam. So we've got 1, 2, 3, 4, 5 different things going on. Let's go ahead and plug all those in. So Q here is going to be equal to, we want MC delta T. So we need that for the ice. So this is 1 times 2.1, and then our temperature change is 20. Plus we have 1 kilogram, and we've got to go through that latent heat of fusion, which is 333.7. We're going to add that to MC delta T for the liquid, so that's 1 times 4.186 times 100 degrees. Plus, we now need to vaporize all of that, so that's 1 kilogram times 2,256 units. Plus, and then we're going to change the 1 kilogram of water, of steam. We're going to go ahead and 2.01, we're going to increase that by 10 degrees. So now that we've done all those things, that'd be 3,100 kilojoules of energy. That is a tremendous amount of energy in order to heat ice all the way up to steam at 110. For the next problem, this is for thermal conduction. I've been given a slab of material, has a 1 square meter thickness area and a thickness of about 2 times 10 to the negative second meters. They want to know what is the thermal resistance. So for letter A, our thermal resistance is equal to the thickness divided by that kappa value times the area. So this is 2 times 10 to the negative second, that's the thickness. The kappa value here is 0.17, and then we have an area of 1. So this one is 0.12 Kelvin per watt. For letter B, our value is equal to the same thing again. And so we have 2 times 10 to the negative second. But this time, for iron, we would have a value of 80.2 times 1. And that would be 2.5 times 10 to the negative fourth Kelvin per watt. And then finally for letter C, R is equal to D over kappa L times the area, and then this last one is for copper, so 2 times 10 to the negative second over 401 for copper times 1, and that would be equal to 5 times 10 to the negative fifth Kelvin per watt. For number 56, we have a hiker. This is a great problem. Wearing wool clothing, has a 0.5 centimeter thickness to keep her warm. Skin temperature is 35 and the outside temp is 4. Her body surface area is 1.2. The thermal conductivity wool is only about 0.04. What is the rate of heat conduction? So this is why people wear wool. As long as you don't get it wet, you're going to find out why here in just a second. So for letter A, they want to know what is the radiant heat conduction, so that's our power. That's equal to this kappa times area delta T over the thickness. So we have 0.04 for our thermal conductivity. We have 1.2 square meters, and then we're going to have 35 minus 4 for our temperature change, differential over 0.005, because this needs to be in meters, so 0.005 for our thickness. And that will give us 300 watts. So for letter B, now we're going to do it when that wool is wet, and that will change our K value. K value now is 0.6. All the other numbers stay the same, so this would be 35 minus 4 all over 0.005, and now we end up with a whopping 4,500 watts. So don't get that wet. That's not a good thing. You can kind of think about Civil War times and what they went through. For number 63, this talks about a black body. It's radiating at 1650 K. They want to know what is the maximum, what is the wavelength has a maximum intensity. So here, wavelength maximum intensity times T should be equal to our constant 2.898 times 10 to the negative third meters times Kelvin. So here, our maximum is equal to 2.898 times 10 to the negative third, all over 1650 Kelvin. That's our temperature. And we end up with 1.76 times 10 to the negative sixth meters, which is 1.76 micrometers. And that is our final answer for 63. For the next problem, which is number 66, this one's dealing with a light bulb. It has a tungsten filament heated to about 3 times 10 to the third Kelvin when you have electric current. If the surface area of the filament's only about 1 times 10 negative fourth square meters, has a emissivity of about 0.32, they want to know what is the power in the bulb. So here the power is equal to E times sigma times A times T to the fourth. So our emissivity here is 0.32. Our value for sigma is 5.67 times 10 to the negative eighth. Okay, that's for that tungsten. The area here is 1 times 10 to the fourth. And then finally, our temperature here is 3 times 10 to the third to the fourth. If you do all that math, you should get this is a 150 watt bulb. The very last problem that we're going to look at here is number 69. It is a student who wants to lose some weight. He knows rigorous aerobic activity uses 700 kilocalories per hour or 29 kilojoules per hour, and it takes about 2,000 kilocalories per day or 8,400 kilojoules just to support biological functions to keep his body warm. He decides to burn calories faster by sitting naked in a 16°C room, so he can radiate all of those calories away. So his body has a surface area of 1.7 square meters. His skin has a temperature of 35°C. We're looking at an emissivity of 1 since he's not wearing any clothes and he's just radiating all that heat out. At what rate will the student burn calories? So we know that now we're looking for the net power here. That's equal to, because he's both absorbing and emitting, so E sigma alpha, and then we have our temperature minus our temperature here. So this is equal to 1 times 5.67 times 10 to the negative eighth times 1.7. So here, this first temperature is 308.15, and that is his body temperature. So body temperature minus the temperature, remember S here is surroundings. This is to the fourth minus 289.15 to the fourth. So where did these temperatures come from? Well, remember, to get these temperatures, we're just going to say T is equal to 35 plus the 273.15, and then this temperature is equal to 16 plus 273.15. 0.15. All right, so now we kind of know where they're coming from. We're going to end up here with a net of 195 joules per second, which is essentially watts. But the reason we keep it in joules per second here is we want to convert it in kilocalories per hour. So 195 joules per second, and then I've got 1 kilocalorie per 4186 joules, and I know that there are 3,600 seconds in 1 hour. And so if you do that math, you should end up with 168 kilocalories per hour is what that person is losing while they sit there in that room. And that is the end of your problems.